Yeah. Okay. Hi, everyone. Welcome to the Lunar Geology in Landers section. Our first talk is by Lingzhi Sun on the multispectral imaging and hyperspectral profile of the first dissection for core 73002. So take it away.
Okay, thanks. So today I will introduce some preliminary results from the spectral measurements of the first dissection for the Apollo 17 core 73002. So this core was collected at the Station 3 during the Apollo 17 mission, and this station is located on the light mantle down the South Massif next to the Lara crater. Here I have a panorama of the Lara crater. So the core is collected in here, and there are also some trench soils collected next to it, which can be used as reference soils for this core. So the double drive tube is now curated at the Johnson Space Center. The whole core is about 60 centimeters in length. So the lower segment is the 73001, and it's sampled about 70 centimeters in depth, but it haven't been opened yet till today. So here is the look of the 73002. It's the upper segment, and it is sampled about 30 centimeters in depth. So when it's extruded from the tube, it's compressed to about 18 centimeters. This core was opened in last December. Our role is mostly measure the spectral data for this core. So the whole core is curated within this glove box. If you look at the schematic diagram on the right, we have to observe from the through the glass wall of this glove box, which limited our measurements to only at visible and near infrared wavelengths. So we have two sets of measuring systems. One is the multiband imaging system, and the other is the hyperspectral system. So for the multiband imaging system, we covered the wavelengths that is similar to the Clementine ultraviolet visible camera, and the hyperspectral system is covering 500 to 1700 nanometers. So this figure is on the left is the photograph of the whole core, and the red circles are the hyperspectral footprints along the core. The two figures on the right are the multiband imaging results. So the middle one is a reflectance image mosaicing of the whole core at 570 nanometers. We can see the systematic darkening effect on this image, and we also made a false colored image of the whole core. The red channel is the 750 versus 415 nanometers, which is sensitive to the spectral reddening effect. And we can see that on this figure on the right, there's this very obvious darkening effect from bottom to top of the core. And these are this spectral darkening and reddening are due to space weathering. So when we plot the whole core over this ratio plot, so the y-axis is the 950 versus 750 nanometers. The x-axis is the 750 nanometers. We can see that there's not a lot of variation along this iron axis, but along this optical maturity axis, there's a wide span. So we used these equations to calculate the iron abundances and OMAD values, and also the titanium abundances. Then we derived these maps. So the top one is the optical maturity. So on the left side is the top. From bottom to top, we can see this increasing in maturity. But for the iron and titanium, we don't see a lot of variation. It's pretty homogeneous along the whole core, suggesting this core might be sampling the same regolith stratigraphy. So when we plot the OMAT variation along the whole core, we can see that the most fresh soils occurs around 2/3 from the top, and that's about 20 centimeters of the original sampling depth. And when we apply this sampling regolith reworking depths to the equations derived by Dr. Morris et al., we can derive this regolith reworking time at 135 million years. And this is consistent with the cosmic re-exposure time of rocks collected at the same station to the core. And for the hyperspectral measurements, we can see something similar to what we observed from the multispectral data. That is the systematic darkening, and when normalizing the data to 750 nanometers, we can see this reddening effect. But there's no obvious weakening of spectral bands. Might be the reason of these narrow iron abundances along the core, or it's influenced by the grain size variations along the whole core. So we developed a radiative transfer model that can mix both minerals and chemistry at the same time. So when we apply this model to the hyperspectral data we measured, we can see a lot of plagioclase and low calcium pyroxene. And so the blue circles are from the modeled mineral abundances, and the red dots are from the XRD measurements of the model abundances for the reference soils collected next to the core sample. We can see a good consistency from these two data sets. And the magnesium number we derived is 61, which is consistent to those soils collected at the same station. To conclude, we observe systematic darkening and reddening from both multispectral images and hyperspectral profile. We mapped the iron and titanium contents for the core, and no obvious conventional stratigraphy is observed. So from the OMAT variation, we derived a regolith reworking depth at 20 centimeters, corresponding to 135 million years of reworking time. The model abundances derived from radiative transfer modeling and hyperspectral profile show abundant plagioclase and also pyroxene exists within the core. And with that, it's the end of my presentation. Thank you for listening.
Okay, thank you for that, Lingzhi. The floor is open if anyone has any questions for our speaker. Okay, we have a question. The core was taken from a landslide deposit, yes. Do you attribute the homogeneity to a landslide or just to a regular regolith processes?
Oh, I think this homogeneity is one because it's on a landslide, and also it's kind of on the ejecta of this lava crater, so kind of both.
All right, thank you, Lingzhi. Before we continue on, I did want to take a moment to congratulate you on the successful defense of your PhD thesis yesterday.
Thank you.
I can't speak for everyone, but I can absolutely assure you that I would not have been able to give a presentation the day following my PhD defense. So I am both very proud, and I want to take a moment to congratulate you publicly for an awesome job both yesterday, of course, and today. And I assure you that eventually we'll be able to hold meetings and we'll be able to congratulate you in person. But for now, a virtual Zoom salute for you. Congratulations.
Thanks.